This is the third lecture of this week. In the first two lectures, we derived the for governing equations and the boundary conditions, stress based governing equations for torsion problem in elasticity. Today, we will just demonstrate those equations and that formulation through one example. Now, the example that we will be solving today, just before that example, if you recall, these are the summary of the entire thing that we discussed in first two classes. This is the assumed displacement field. It comes with the, though in the previous class we discussed the summary, just to keep the continuation. This displacement field, it's starting from the assumption that your angle of twist is linearly proportional to the length of the or the length direction. And this is the stress function. We define stress function as this, and then finally the governing equations for this is a Poisson's equation, which is this one. And this is important, the traction boundary condition on S. The direct interpretation of the traction boundary condition on S is del psi del S ds is equal to 0. It tells you that psi has to be constant on the surface, and we can take that constant value is 0. So, that psi is vanishing on the surface, and this is the traction boundary condition on the ends. Now, if you take psi vanishes at the surface, then other traction boundary condition, the stress free boundary condition, that automatically vanishes on the surfaces. Okay. Now, let us start with this example. This is the example that will find out expression, what are the torsion, what is the angle of twist, what is the displacement, out of plane displacement, all these expression that we find out for this problem. Now, this problem, the reason why we are starting with in the subsequent classes will be solving few other examples as well, but the purpose of particularly taking this example as our first example is, you see, we already know the solution of circular shaft under torsion. We already have the solution from strength of material, right? Now, whenever we derive that solution, we had certain assumptions, and if you recall, our starting point of entire discussion that we have been doing, the starting point was some of the assumptions that we had in case of circular shaft, some of the assumptions are not valid, and the plane section remain plane, there is no out of plane deformation. Those assumptions, and every section rotates as a rigid body, those assumptions are not valid if your section is non-circular section. What we do is, we will try to find out the solution of this example, and then in the limiting case, when A is equal to B, it becomes a circle, we will see that whether we get the solution that we obtained from strength of material. Okay. So, let us start. If you recall, the first step of this is, we have to start with an assumption of psi, and we take the assumption, we take the expression of psi such that it vanishes at the boundary. Now, what is the equation of this boundary? Equation of this boundary is x square by s square plus y square by b square is equal to 1, right? This is the expression. Now, assume psi as some factor k into x square by s square plus y square by b square minus 1. If you take psi as this, then automatically, irrespective of the value of k, automatically it vanishes at the boundary. So, we will take psi as this. Okay. So, let us do this exercise now. So, we have psi is equal to k. K is a constant that we need to find out, is x square by s square plus y square by b square plus y square by b square minus 1. Okay. So, this is psi. Now, psi has to satisfy the traction stress free boundary condition is automatically satisfied by this. Psi has to satisfy the governing equation, which is the Poisson's equation. And what is that Poisson's equation? If you recall, del 2 psi del x 2 plus del 2 psi del y 2, that should equal to minus 2 mu alpha, where mu is the shear modulus and alpha is the angle of twist per unit length. Now, if I substitute that the entire expression of psi in this equation, what we get is the first one will be 2k by a square, and the second one will be plus 2k by b square, and then we have minus 2 nu alpha. From this, if we find out the expression of k, the expression of k will be minus a square b square mu alpha divided by a square plus b square. Okay. This is the expression of k. So, this expression is the psi when k is equal to this, it satisfies traction free boundary condition, it also satisfies the governing equation. Okay. Now, another boundary condition is what? Another boundary condition is the condition at the end where you have the torsion. Means if we take this, so we have already specified we have already specified boundary condition here. We have already specified boundary condition here by taking expression of psi as this. We already had the psi already satisfy the governing equation. Now, another thing is we have to, the psi has to satisfy the governing equation, this boundary condition here. What is that condition? This condition tells you that torque at this point is equal to T. So, if you recall, the condition was, another condition was the torque, if we write on that boundary, T was equal to 2 into integration over r over the entire cross section into psi dx dy. Now, psi was this. If we substitute this psi in the expression, what we have is then T is equal to 2k, which is then integration of r, integration over r, then x square by s square plus y square by b square minus 1, then dx dy. Okay. Now, let us write all these expression. We had 3 terms in the expression. Let us write them separately. What is that? This gives you x square 1 by take a square out. So, this is essentially x square dx dy plus, if we take 2k by b square out, then this gives you y square dx dy. Now, then finally, we have tk integration of dx dy over r. Now, look at this term. You are already familiar with this term. What is this term? This integration of this term. This term is essentially, if this is the ellipse, this term is essentially area of that ellipse, right. So, this is the area of this ellipse, cross section area of this ellipse. Now, look at this term. This is, if this is the x axis and this is the y axis, then this term is essentially second moment of area about x axis, right. So, this term is second moment of area about Ixx or Ixx. And what is this term? This term is essentially second moment of area about y axis. So, this is Iyy, right. Now, for an elliptical section like this, we already know these values. This area is equal to, so we already know the integration of this value. Area is equal to pi into AB, and then first the second moment of area about x axis, that is equal to pi by 4 into a b cube, and then Iyy essentially gives you pi by 4 into b a cube. So, essentially these integrations are this, and if we substitute these a Ixx and Iyy in this expression, this expression becomes finally, this expression becomes 2k by 2k into this is ixx by iyy by iyy by a square, iyy by a square, and then please this become ixx by b square, and then this become minus this one minus area. Okay. So, this is equal to T. So, T is equal to this. Okay. Now, if you substitute Ixx, Iyy area from this expression, and then final expression of T from this becomes T is equal to pi, you can verify this, a cube b cube and then mu into alpha divided by a square plus b square. So, this is the expression of this. Okay. So, from this expression we can also write what is the expression for alpha, then alpha will be T into a square plus b square divided by the same thing pi a cube b cube into mu. Okay. This expression is also important. So, we have. Okay. So, we already determined what is the amount of torque we have, what is the relation between torque and the angle of twist. Okay. Great. Now, you see the whether it is circular cross section or non-circular cross section, one assumption we kept same, and that assumption is the angle of twist is linearly proportional to the coordinate axis, longitudinal axis. Okay. Now, once we have the angle of twist, let us find out what are the stresses we have. Now, if you recall the expression for stress, is sigma xz as a function of that's how we define the stress function, that is del psi del y, and sigma yz that is equal to minus del psi del x, right. Now, psi is equal to again same 2k x square by a square plus y square by b square minus 1, and if I substitute, we already have an expression for k we determined. If we substitute that expression in this substitute the expression of psi in this stresses, so finally we get xz is equal to, I leave it to okay, this becomes minus 2 a square mu alpha divided by a square plus b square into y. Okay. And then this become the other stress component become yz, that become 2 into b square mu alpha divided by a square plus b square into x. Okay. Now, already we have the expression for torque, this torque, and if you substitute this expression in the expression of stresses, then this expression can be again further rewritten as minus 2 T y by pi a b cube, and then this 2 T x by pi b a cube. So, this is the expression for stresses. Now, let us find out what is these are the stress components. If we have the cross section is this, and this stress component, this is x direction, this is y direction, x and y. The direction of xz, it is acting on it is in this direction, this, and yz will be in this direction. So, it is acting on a plane perpendicular to the normal to the y axis. But the direction of the stress is direction of the perpendicular to the z axis, and the direction of the stress is either in x direction or in y direction. Then the total stress, since for both the stresses they are acting on the same area, the resultant stress will be, if you say the resultant stress, the total resistance stress, let us write tau, because that is how that is the symbol we used in strength of material while calculating shear stresses for circular shaft. This will be sigma x z square plus sigma yz. Please recall, we do not take the component of stresses like this. We can take the component of forces, not the stresses like this, but since both the stresses are acting on the same area, if we convert them into force and take the component, it will be same, right. So, this is if you substitute this value, the final expression will be 2t by pi a b into x square by s square, x square by e to the power 4 plus y square by b to the power 4. This is the expression for tau. This expression is also important. So, this expression, it tells you how tau is varying over the entire surface. If you take any value of x and y, how tau is varying over x and y. Now, what is the maximum tau? Maximum tau we can this is the expression of tau, we can differentiate with coordinate axis and then find out for which value tau is maximum. And if you do that, for this case, since a is equal to b, a is the major axis, b is the minor axis, for this case the tau max, the expression for tau max, you can determine this expression for tau max will be 2t by pi a b square. This you can determine by differentiating it with respect to the coordinate axis and then find out and make them 0 and then find out what is the value of x and y for which this tau is maximum. Okay. So, this is the expression for tau max. So, already we have determined the torque, the angle of twist, the expression for tau max. What is left is what is the displacement, the out of plane displacement. Okay. Now, the out of plane displacement, let us find out out of plane displacement. If you recall, we had two this expression, the sigma z is related to displacement sigma x z that equal to mu into del w del x and then minus alpha into y, right, and then sigma y z is equal to mu into del w del y plus alpha into x, that is the relation we already had, right. Now, then just now we had an expression for sigma x, this is sigma x z and this is sigma y z, this expression just now we had these two expression, right. Now, we can substitute these two expression in these equations and then from the first equation you differentiate this the entire thing with respect to x and then get a constant which is a function of y, and then from the second equation we can get that constant. We have done it before. Whenever we have this kind of function, this strain, from strain we had to find out displacement, we integrated the strain with respect to that coordinate axis and then we had a constant which is the function of say other coordinate axis and then another equation we use to get those constant. We have done it in the previous, and if you do that exercise, I leave it to you. If you do that exercise, the expression for w will be t into b square minus a square divided by pi a square a cube b cube. This expression is interesting, x into y. Okay. Now, this is interesting. Okay. This is the expression of w. So, we already have an expression for w. Now, you could recall how to get an expression of u and v. U, it depends on u depends on u depends on alpha. Expression alpha already we know, and therefore, if you recall. If we recall, this is the expression we have. So, alpha for already we have an expression for alpha. If we substitute alpha here, we get expression for u. If we substitute alpha here, we get an expression for v, and just now we have obtained the expression for w. Okay. Now, so let us summarize the solution that we have. This is the problem that we discussed, and this is the. Now, if you plot the expression for w that just now we had, if you plot the contour, it looks like this. Okay. Now, so this is the summary of this equation that we have just now. Okay. This is the torque and this is tau max and this is the w. Now, let us find out from this solution what the solution is for a circular section. Now, if the solution, if it is a circular section, then what happens for a circular section? For a circular section, your A is equal to B, let us that is equal to R. Okay. Now, substitute A is equal to B in this expression, but before we do that, recall, okay, let us first do that. If we do that, then what would be the expression for T? Expression for T will be, now then we have to, after the substitution, we have to compare the solution with the solution that we have in case of strength of material. Now, T will be, if we do that, then T, final expression of T will be, let us, I have this expression with me, this will be pi, and then this will be r to the power 4, r to the power 4, and then mu into alpha divided by 2. Okay. And then what you have, then alpha will be, this gives you alpha will be 2 t, or let us just write t into t divided by mu into then pi r to the power 4 by 2. Okay. This is the expression for alpha. Then what is the expression for tau max? Then tau max will be 2 t divided by pi r to the power r cube. Okay. And then what is the expression for W? W will be, if you substitute A is equal to B here, it will be 0. Now, these three expression is important. Now, you recall what we had in the case of what expression we had in the case of circular shaft, that alpha by alpha, which is your angle of twist per unit length, that was T by G into J. What is G? G is the shear modulus, mu is the shear modulus. What is J? J is the polar moment of inertia, and this is the polar moment of inertia for a circular section is pi r to the power 4. So, these expression and this expression is same. Similarly, this is the expression that we had for tau max in case of a circular section, and for a circular section W is equal to 0, there is no warping takes place, there is no out of plane displacement. So, what we have seen here, you see, we already had the solution of circular section, and when we had the solution, that solution was based on certain assumptions, and those assumptions are valid for a circular section, and we just verified this. Those assumptions are valid. There is W is equal to 0. There is no out of plane displacement if the section becomes a circular section, which is very consistent with this solution. Now, if the solution, if the section is not a circular section, here in this case W is not 0, and therefore, we have some out of plane displacement, and therefore, that assumption cannot be applicable. And in fact, when we derive this equation, we never had that particular assumption. Okay. So, next what we do is, next we will again apply the same thing, same formulation to other problems. Other problem means problem with other cross section. We will see if the cross section becomes a triangular cross section, if the cross section is a circular cross section, is a rectangular cross section, then what happens to this, how to choose psi, and then how to do this exercise for those cases. Then we will also see, you recall all these examples, this example, or they take the example of a triangular section, rectangular section, all these examples, your cross section is a simply connected domain. Now, consider a case that you are interested to find out what happens to a pipe. Okay. And you take a pipe, these are all solid shaft, but if you take a pipe and then you apply some torque, then what happens? And if you take the cross section, that cross section is not simply connected domain. So, we will also see what happens in those cross section, how to deal with these equations and how to assume psi for those domain. So, we will do that in the subsequent week. So, I stop here today. Next class we will discuss few more problems with simply connected domain, and then we go for the domain which are not simply connected. Okay. See you in the next class. Thank you.